action. All right. All right, so let's go ahead and get started. First off, thank you everybody for coming. I know it's late, but hopefully we'll be able to get through some good material tonight. So this is going to be the first of a two-part session to try and get you all ready for the FE for the sections that are focused in structural engineering. So tonight what we're going to do is cover some fundamental topics in structural analysis, and then next week I'll do some stuff with structural design. I'm going to do steel and concrete in the same session. And one of the things that I will emphasize tonight and next week is, we're going to spend some time discussing this topic tonight, but it's really only going to amount to about 6 questions on the test. So I don't want you to think that any one topic is a big deal, okay? Let me go through some of the topics that I'm covering tonight. I'm ultimately going to cover forces in structures and deflections in structures. That's going to be the main focus of tonight. But one of the things I'll mention is everything that we're going to do tonight is statically determinate. Okay? We're not going to do any indeterminate problems, no moment distribution, because the chances that you're going to get a problem like that on the exam are fairly slim. Because the thing about indeterminate analysis is it's not so much a hard problem as it is a long problem. Indeterminate problems take a while. I mean, they do. I mean, and when you do the math for the problems on the test, you don't really have that much time. So the problems that you get in each topic are actually fairly basic. So because of that, we're going to do some basic structural analysis problems tonight. Some of them might look a little scary, but in the end, you can do them fairly quickly. And I want to try and show you the tricks of the trade and some of the fundamental tools you can use to attack these problems. Okay. One thing I'll point out, I tried to design a problem for each of these topics except for one. I don't have a problem specifically on support reactions because in just about every problem that you do, you're going to have to compute support reactions. And so we'll get plenty of practice on that. But if you leave tonight and you're unsure on support reactions, then come see me later because I can provide some more material and whatnot. So ultimately, we're going to cover forces in structures, deflections in structures. I also want to cover a problem on LRFD load combos. We actually covered that last semester, the first 2 weeks of steel design and concrete design. That was sort of that catch-up material that we had. And if we have time, we'll cover influence lines. But if we gauge it and we see we've been here too late, we'll worry about it later. So with that, I'm just going to go ahead and get right started into this problem. And I want to make a few observations, just behavioral observations, before we even start doing this problem. Okay? So this is our first example, and it's a truss analysis. Okay? So the problem states that for the plane truss that we have shown here, what is most nearly the axial force in member CG? So we're ultimately looking at this diagonal member inside the truss here. And this is one of those problems where it's kind of tough to look at the choices and see what the answer is, okay? Or what it isn't. Maybe that's a better way of putting it. One observation that might be worth making is, let's say, for instance, on this problem, instead of asking you for member CG, what if I asked you for member BC? What if I was asking you for this member right here? Okay? Now let's just think of this truss as one big structure, and I've got these downward loads right here. Would it make sense that this structure is going to deflect downwards like so? So if I look at these members on the top, just your gut feeling, are those members on the top in tension or are they in compression? They're in tension, okay? So if I asked for member BC right off the bat, there's 2 answers eliminated, right? Okay, that's an important observation to make. This is a multiple choice test, okay? I mean, one of the very important statements in this question is not what is the force in member CG, it's what is most nearly the force in CG, okay? Yes, sir?
Do they check your work, or if it comes time, like crunch time, can you just make guesses, and if you get it right, you get it right?
Yeah, you can guess. I mean, I'm going to be completely honest with you. When I took the FE exam, I mean, I went through and did a first run through and had, an assortment of questions answered, and then I started attacking each topic one at a time. But I got to the point where I was doing the tests and I said, haven't guessed A in a while, and guessed A. And just based off statistics, I felt comfortable that, if I hadn't guessed A in 10 or 20 questions, that's got to be A, even if I didn't know what the answer was. And I don't think there's anything wrong with that, because one of the things about this test is it is a marathon. I mean, when I took it, it was 8 hours long, and for you all, it's going to be 6 hours. That's not going to make it any better. It's a long test, But that's the whole point, is that because it's a long test, you're not going to get asked the most complicated questions on the planet. You're going to get asked fundamental questions in each topic, okay? That's why they call it the Fundamentals of Engineering exam. All right? Is everybody good? Now, here's another point that I want to make about this problem, okay? This problem is asking for the force in a given member, okay? So for the force in that member, let me just ask you, this is a truss analysis, so we could use method of joints or method of sections. Which one should I use? Method of sections. If I use joint analysis, I'm going to be here all day, okay? But if I use method of sections, then this gets a whole lot easier, right? Make sense? All right? Now, theoretically, we're actually going to do this in the opposite direction, but theoretically, if I could cut a section, would it be more advantageous to look to the left or look to the right? To the left? Well, if I look to the left, that means I need to know the support reactions. Theoretically, I could look to the right and never even have to solve for them. Now, the geometry on this truss is a little funky, and plus I figure just to get everybody in the swing of things, we'll go ahead and compute support reactions. But it's just an observation I want to make. You could cut a section, look to the right, one moment equation, you're done. That's it. Okay, so that's one thing I want you to take away from this session. This is a nasty truss. All the members are at different slope ratios and whatnot, but now looking at it, it's just cut a section some moments and you're done. Okay, so I want you to think in those terms, going with that strategy. All right? Everybody good? I'll tell you what, let's do that. Let's cut a section in some months. Let's do that. Let's see what happens. So here's how I'm going to do this. All right? I'm going to escape from this, and I got my little snipping tool. I'm going to copy this image. Let's see how this works. I'm going to paste it onto a notebook. That is way too small, or way too big. Let's see if I can pull it a little bit. And then, how do I make that full screen? All right. Let's see if this works. Hey, it works. Cool. Okay. So what I'm going to do is, let's just go ahead and see how this works. Let's cut a section. So I'm solving for member CG, right? So why don't I cut a section right there, right? And just to illustrate this strategy, let's look to the right. So I'm going to redraw this truss down here, and let's see what I get. All right, so okay, so we've got that, and we've got that, we've got that, and that. And since I've got colors, let's go ahead and use them. So this is 20 kips, 40 kips, 40 kips, right? Can everybody read that? Is that coming out clear? Okay, good. This is my first time using this. Forgot a little diagonal right there. Oh, you can? How? This rough. Oh, there we go. Hey, there we go. I can, yeah, the buttons can change the color up here, so I'm going to use that. Thank you very much. Okay, so here's my truss, the section I cut. Now, I don't have any unknown support reactions, but I've got 3 unknown forces in each of these members, right? Everybody good with that? Now, the first thing that I'm going to do is I'm going to make a blanket assumption. This is a strategy for the test. I'm going to assume that every one of these forces, did it again. I'll just leave it like that. I'm going to assume that every one of these forces are in tension. Okay? Now, there's a reason why I'm assuming that. Okay? First off, I know that that's not going to be the final answer. For instance, we agree that this member up top is going to be in tension, but this lower member here, this GH, is probably not. It's probably going to be in compression, but that's okay. Okay? I'm drawing all of my arrows in tension. Why? Because if I sum moments or sum forces and I get a negative answer, it means my assumption is wrong and the member's in compression. So it's an easy way of doing my bookkeeping. Just assume everything's in tension, and if something comes out negative, it's in compression. So it reduces the error. All right? Now here's another thing that I like to do. Okay? So this force down here, we'll call this GH. This force here, we'll call this CG. And this force here, we'll call this BC. Any force that is diagonal, I like to split it up into horizontal and vertical components. So we've got a let's see. Oh. I have this horizontal component, we'll call this CGX. We'll call this component CGY. I'm going to erase this so I can draw a little clearer. This is BCX, and this is BCY. Okay? I like to go ahead and do that right off the bat. Okay? Is everybody good? Okay. Now, all right, so that's essentially our section, and I'm not going to draw the dimensions because I've got the dimensions shown right above right here. Okay? So what we've got to do is we've got to attack this problem with a little bit of strategy. Now, you cut a section for one simple reason. You cut a section because you want to sum moments. Okay? So where should we sum moments? Well, you want to sum moments where two of your forces coincide. Okay? So what seems like an obvious place to sum moments? I don't know, maybe point C is an obvious place. We could sum them at point C. We could let's sort of identify where we could sum moments. Okay? We could sum them here, right? At point G. We could sum them here at point C. There's actually another place that I'm not going to do for this problem, but there's another place that you could sum, and that's all the way out here, because you're going to have BC and GH coincide, and that actually, from a strategic perspective, would make more sense. The geometry is a little funky, and since it's our first problem, I'm not going to do that, but it's just something I wanted to point out. Okay? All right. So where do you all want me to sum moments? Do you want me to sum moments at G or at C? You tell me. It doesn't matter. So, okay. We'll do G. All right. All right. Now, for those of you that have had me for a structural engineering class or structural analysis class, which is, I don't think anybody in here, I sum moments a little differently. So this is what I like to do. I say sum of moments about point G equals 0, and then what I do is I draw myself a little table. And I say that all the moments spinning that way have to equal all the moments spinning that way. And then I just go through, and like a bookkeeping operation, I just start tabulating them down one at a time. So watch this. So I'm summing moments here. I'm looking at this upper truss. I'm summing moments right there. See that little green spot I'm drawing? Okay, so let's handle these one load at a time. So I'm looking to the right. So we'll start off with that one. Okay? So what do we say? We got 40 kips. Is that going to belong on the left side of the table or the right side of the table? Which way is that going to rotate point G? Left. Okay, so I've got 40 kips. Oh, I had that fixed. So I've got 40 kips acting at what moment arm? 20 feet. So you can start to see how this is going to go. So let's keep going. So we've got the first 40 kips. The second 40 kips is going to do the same thing, right? And that's at what distance? 40 feet. And then the next one is what? 20 kips times what? All right. So far, so good, right? So that takes care, if I'm checking that off on my section, takes care of that one, and that one. Okay? I don't have to worry about GH, do I? That goes through G, right? I don't have to worry about any of these CG forces. I got to worry about BCX and BCY, right? Okay? Well, watch this. This BCX and BCY, I can move it up and down this line, right? Remember, principle, transmissibility, as long as it's acting along that line, it can move wherever. Okay, watch this. I'm going to move those forces here and here. So we've got B, C, Y, and B, C, X. Now, why did I do that? Exactly. You don't have to deal with BCY. BCY goes right through that point. So the only thing I have to deal with is this one right here, BCX, right? Now BCX, which side of the table does it belong? The left or the right? Right. So BCX, and what's that moment arm going to be? Now it's interpreting the dimensions of the truss a little bit. So this first member is 10 feet, and this last one's 30. So would you agree 10, 15, 20, 25, 30? So what's the distance? 25. So far, so good? So when you say sum of moments equals 0, basically all you're saying is that everything spinning clockwise has to equal everything that's spinning counterclockwise. So on the right side of the table, I've got BCX times 25 feet. And on the left side of the table, I've got, was that 40 times 20? Let's see, 40 times 20, that's 800. 40 times 40, that's 1,600. 20 times 60, that's 1,200. So 800 and 1,200 will give you 2,000, so that's, what, 3,600? I do that right? Okay, so there's your sum of moments right there. So, therefore, BCX is what? That's 3,600 over 25. What is that? 144. Now, mathematically, did that number come out positive or negative? Positive. So since that number came out positive, it means that the direction we assumed for BCX is correct. And if BCX on our diagram is drawn to the left, that means that it is 144 kips to the left. So far, so good? Okay. Now, the reason why I split things up into X and Y is because once I get one component, I can go ahead and get the other one. Now, how do I get the other one? I use the slope ratio. Okay, so let's take a look at this slope ratio. All right. We're looking at member BC. Maybe I should go ahead and put that. Come on, go away. Put that up there for now. All right. Let's look at member BC. So here, let's say this is member BC, and we've got a slope ratio. Basically what I'm trying to do is record rise over run. So would a fair way of recording that, would it be 80 to 20? Or a simpler way, 1 to 4? So would a fair way of writing this is BCX is to 4 as BCY is to 1? Would that be a fair way of writing it? So therefore, BCY is 1/4 BCX, which is, if this is 144 kips, what is 144 divided by 4? It's what, 36? 36 kips. And as for the direction, since BCX came out positive, BCY does as well, and we drew BCY acting up, which means it does act up. How are we doing? Everybody feeling good so far? It's not too bad, is it? That wasn't my fault. Okay. Extend page button. Okay. So we've got, let's just go back to our free body diagram and let's see if we can explore what to do next. Okay? Now, we did all this summing moments at G because it eliminated 2 of our unknown forces and left 1 of them. Okay? So now let's go back to our free body diagram and let's see if we can determine what to do next. So what do we do next? Well, we know this one and we know that. We know BCX and BCY. So how many remaining unknowns do we have in the horizontal direction? How many remaining unknowns do we have in the vertical direction? 1. So what that means is what we should probably do is sum forces in the y direction. So move that over there. Okay. So I do this the same way. I draw a little table and I say everything going up has to equal everything that's going down. And I start going off of my diagram and I just start filling it in. So let's see. Let's just start tackling this one by one. Okay, BCY. BCY is going up, right? And it's still going up because my answer came out positive. So I'm going to put BCY equals 36 kips. And I put that in the up column. All right? What about going down? I've got CGY going down. So that's CGY here. Now, I don't know what's going on with CGY. All right? What else do I have going down? Well, going down, I've got 40 kips, 40 kips, and 20 kips. Is that everything? Did I miss anything? No, I got that right here. So that's everything, right? So here on the left side, I've got 36 kips, and on the right, I've got CGY. Oh. Just go ahead and draw it like that. CGY plus, what, 40 and 40 is 80, 20 is 100 kips. Okay? So therefore, what's CGY going to come out to be? Negative 64 kips. So if it's negative 64 kips, that tells us a couple things. First off, okay, right off the bat, that tells us that 64 kips is acting in what direction? Up. Okay? Now, let's just go back to the problem. Anytime you're doing this stuff, you want to make sure that you're going back to your problem and referring to that. Here's the problem. What's the problem asking for? Force CG. Let's put, okay, there, okay, you've made a couple observations right off the bat. All right? The answer came out negative. What did we assume for all of our forces? That they were in? So when it came out negative, compression. Okay, so we know it's in compression. And the number we just got was 64, right? Which means it can't be 45.3. So from a strategy standpoint, we could stop right now, couldn't we? What's our answer? It's C, right? Now, for completion's sake, let's go ahead and just finish our problem and see what we get. All right? So I'm going to go use the slope ratio again. Let me scroll up here a little bit. So if I look at member CG, that change in horizontal distance is 20. What about the change in vertical distance? 20, right? So it's a 1-to-1, right? So if I draw that member out, that would be 1, 1. Y'all remember what the hypotenuse is? Square root of 2, right? So if I start to try and write an expression, would you agree with the following statement? Would you agree that CGY is to 1 as CG is to the square root of 2? Do you agree with that? So therefore, CG is CGY times the square root of 2, which is 64 kips times the square root of 2. And what is that? 90.5 kips. And is that tension or compression? Compression. Yeah, we've already made that observation that based on the fact that our answer came out negative, we just know it's in compression.
So why would we do it? Why would we want to do it to the arbitrary point to the right of?
Well, you could. Let me say this: if you're comfortable with all the dimensions and the slope ratios, do it. You know, I wanted to some moments at G because I don't know. Every time I've ever encountered students who've done this stuff and I never taught them, they usually feel comfortable with those common points. So it's like, you know, let's just some moments where it feels natural to some moments. But yeah, absolutely, you know, if you want to go to the original truss and you can say this member has the entire member over here has a rise over run of 80 to 20, so you can drag this out and say if you're dropping down 10, that's 40 feet, and then just some moments out there, you're more than welcome to do that. And then you'll get the right answer. But there's something to be said about us just going through the rigmarole of doing a section analysis, using equilibrium, sum of moments, sum of forces in the y direction, slope ratios, to get us thinking about structural analysis. And I thought that exercise might be pretty good for us. All right. Does anybody have any questions about this problem? Now, we have another truss problem coming up where we're going to do truss deflections. And if you all remember from structural analysis, in order to calculate truss deflections, you have to use the unit load method. You put a 1 kip force on there, and you have to do 2 truss analyses. So we're going to have more experience with truss analysis. So don't worry. We'll have plenty of experience. All right. Okay, so is everybody good with this first example? Did you all have any questions? I mean, please, I want to explore these concepts if you all have any questions. This is the time to say, hey, that didn't make any sense to me. Oh, no, well, whatever question. That's fine. Go ahead.
Is there a way to get the answer C
Mm-hmm.
from just looking at it from the very beginning? Now we've gone through, is there a way to get C right off the bat just by looking at it?
I'll say this. It's a little more difficult for the internal diagonals as it is for the top and bottom chords. Okay? Now, if you do enough truss analysis and get familiar with that behavior, you can recognize that because the diagonals are facing this way, that they're going to be in compression. If the diagonals inside were going like this the other way, they would be in tension. And it just comes from, you know, doing enough truss analysis that you sort of start to see the patterns. But the easy ones to see are the top and bottom members. I mean, just think about this truss as if it was a big old beam with holes in it, okay? If I take a beam and I bend it like this, the top's in compression, the bottom's in tension, right? Well, this is sort of the opposite scenario. Think of it as a beam that was being bent. It would be bent like that, right? Top's in tension, bottom's in compression. It's very possible that on the FE, you might get asked a question where instead of looking for this member, they're looking for this one. In that case, just say, hey, it's not in compression. And there's two of your potential answers gone. Does that make sense? No, those are good questions to ask, really. That's the type of stuff you want to ask.
Could you quickly cover, we don't have to go through everything, but just if we were to solve it at the point outside to the right?
Sure, sure.
You can solve for CG correctly, well, CGY and CGX.
Yeah. I can show you that real quickly. So,
But there should be a lot less calculations.
yeah. So let me do this. Let me make another page. Okay. That one's getting kind of messy. All right. So I'm still going to cut a section at the same place because I'm still after CG. Okay. But here's one point I want to make. Would you agree that, oh goodness, let me erase that. Would you agree that each one of these diagonals are at a 1 to 4, all of them? Okay, so this distance here is 10 feet, right? Okay, so if I erase this and I draw a line, now, I have my pen, there we go. If I draw a line out here to where these 2 points intersect, would you agree that that distance is going to be 40 feet? Because if I drop 10 feet, I got to go out 40 feet. Okay? So if I cut a section, I'm going to have, let's see, this and this. Let's see, that and that, that and that. I'm going to have that. Bless you. Okay. And then I've got my point out here in space. We'll call it point X, whatever. This dimension is 40 feet. Just to have that there. Okay, now let's start writing our unknown forces. So now we've got this GH, but that's going to go right through it, right? Okay, we've got BC, but BC is going to go right through it. Okay, now can I be just a little clairvoyant and assume that CG is in compression? Can I just be a little clairvoyant with that? All right, so would you agree that its X component's going to go like that and its Y component's going to go like that? Now watch what I'm going to do. I'm going to take those forces and I'm going to slide them on down there. So we got CGX, CGY. Everybody with me on that? Okay. So let's sum moments at X. So I've got 20 kips. Does that belong on the left side or the right side of the table? Right side. There we go. Y'all are picking this up, no problem at all. 20 kips times what distance? 40 feet. Okay, I got 40 kips times what distance? I got 40 kips times 80. All right. Okay, so let's sort of make sure we're good on this. So the BC, we don't have to worry about that, right? We don't have to worry about the GH. Do we have to worry about the CGX? No. Okay, all we have is CGY. which is acting in this direction. So obviously, CGY. And what's the distance? 100. All right. So CGY times 100 feet. I think this handwriting is going to be on YouTube. This is horrible. So 20 times 40, that's 800. 40 times 60, 2400. 40 times 80, 3200. So 3200 plus 800 is 4000. That gives you 6400. Okay, so CGY is 64 kips acting up. 3, 2, 1. What do you think? So now are you starting to feel a little more comfortable about this stuff? That's what I'm after tonight. I want you all to feel comfortable about this stuff. Okay? So far, so good? Remember, forces pull along the same thing. Like here's the concept. If you're holding a rope and I'm holding a rope, and you're pulling with 20 pounds of force and I'm pulling with 20 pounds of force, there's 20 pounds of force in that rope. It doesn't matter if we're this far away or if you're on the other side of 3rd Avenue. In the end, it's still 20 pounds of force. So it can, as long as it's moving along that line of the rope, it can be as much as it wants. All right? Everybody good? Okay. Now, as Monty Python used to say, now for something completely different. All right? That would be, wasn't that Mr. Bean? He was a Mr. Bean fan, wasn't he? Well, the guy who played Mr. Bean had a master's degree in electrical engineering. All right, so now what we're going to do is we're going to look at another type of internal force calculation, which is shear and moment. So the problem's asking, let's go through this. So for the beams shown below, what is most nearly the largest magnitude of bending moment due to the applied loads? What's not the answer?
0.
Hey, that one's just right off the bat. That doesn't, make any sense. But these other ones, it's a little more difficult. Shear and moment's not really something that's easy to just eyeball. Oh, it's 72, or whatever it is. This one, you really kind of just need to go through the motions. So I wanted to design a problem where we just go through the motions of drawing a shear and moment diagram. You all need to be able to do that for the FE. So I thought it'd be a great thing to just go ahead and do. So let's try my little trick again. Let's screen capture that. All right. Let's see, make a new page. Whoa, a little big.
Real quick before we get on, to make this, you said we're not going to do any statically indeterminate, but just so I remember, statically indeterminate would be if you replace the roller with another pin.
Yeah. Now, not technically for this problem because all the loads are still vertical, but what if I put another roller on it? That would be statically indeterminate because ultimately we would have more unknowns than we do equations of equilibrium. Remember that we only have 3 equations of equilibrium if we're dealing in 2 dimensions. We have sum of forces in the x direction, sum of forces in the y direction, and sum of moments. If I give you 4 unknowns, then that becomes indeterminate. Okay? That's a good question. That's a good question. Now, I could throw another roller on this problem and introduce an internal hinge, and it would still be statically determinate. But then the problem starts to get a little messy, and it's like, are you really going to have this on the FE? I mean, it's possible, but again, I'm trying to cover the basics tonight. So, well, I mean, okay, then it's the one everybody guesses. Hey. All right. So I didn't do this on the problem, but I probably should go ahead and say, let's just come up with some naming. So let's call that A. Let's call that B. I didn't do that before, but maybe I should go ahead and do that. So So this is pretty straightforward. We've got distributed loads, we've got point loads, we've got reactions that we need to solve. So you all tell me, where do you want to sum moments, A or B? It doesn't really matter. A? Okay, so we'll sum moments at A. Before we do that, though, let me go ahead and do my due diligence. Let's go ahead and draw in our support reactions. Call that AY. Call this BY. Okay. All right, so sum moments at A equals 0. Okay. Now, before we start doing this problem, I've got these distributed loads. I want to go ahead and handle them right now. Now, what do I mean by handle them? Okay. Well, I've got 6 kips per foot acting over a distance of 6 feet. So if I wanted to represent that with an equivalent point load, what would that equivalent point load be? 36 kips. So this is 36 kips. And if I wanted to do my diligence, how far is it from the edge of the beam to that point load? 3 feet. Okay, what about this 4 kips per foot? It's 4 kips per foot acting over a distance of 16 feet, and that is 64. Okay, so we've got 64 kips, and from the edge of the beam, how far is that from the edge of the beam? 8 feet. So if we wanted, okay, so it's from the edge of the beam, that's 16, so that's another 8. That makes this distance what, 12? Is that right? From 20 kips to the edge of the beam is 20 feet, so that makes that 12. Does everybody see that? All right, so we're summing moments at A, right? So let's just start to handle it one at a time. We don't have to deal with AY, right? So good there. This 36 kips, is it going to go on the left or is it going to go on the right? To the right. And what's the moment arm? 3 feet. All right, so the 20 kips, we got to handle that? Thank you. Yes. Thank you. And then what's that distance going to be? 4 feet. All right, so that takes care, okay, we got 36 kips, got 20 kips. We've got this 64 kips, so that 64 kips per foot is on the left or the right? Left, 64 kips. And that, what's that distance? 16 feet. All right, and then we've got BY, which is on the left or the right? Right? 18 feet. Everybody good with that? Yeah, well, what we did is we just assumed it's acting upward, and if it comes out negative, we were wrong. Okay, so 36 times 3, that's what, 108? 20 times 4, that's 80. 64 times 16, I don't know if I'm that good. 64 times 16? 1,024. So here on the left side, it's 1104. That's foot kips. And that over here, we've got 108 foot kips plus BY times 18 feet. So subtract that out, 1104 minus 108. What is that?
996.
Oh, that's close enough. 996 foot kips equals BY times 18. So yes, I got BY. We'll do 2 decimal places just for the heck of it. 55.33 kips. And that answer came out positive, so that means it is acting in the upward direction. So far, so good? Y'all like the table? Is the table? Like the table? Some people like it, some people don't. All right? So you all have the problem in front of you, so I'm going to scroll down a little bit. All right. So we've got some of moments across, or about A, so what's left? All right. Before I forget, I'm going to go ahead and write here 55.33 kips. I'll put that on the little diagram up there. All right. So I think I'm starting to get the hang of this little pen thingy. All right, so we've got 36 kips acting downward, so that's 36. We've got AY assumed to act upward. We got 20 kips acting down. We've got 64 kips acting down. And we've got 55.33 acting up. Okay, so here on the left, it's AY plus 55.33. And on the right, 36 plus 64 is 100, plus 20 is 120 kips. Looking like we made the right choice on our direction. And AY is, what do we got, 64.67? Positive direction, positive sign indicates we assume the right direction. So if I want to include a number, see, this isn't so bad, is it? Not too bad at all, right? Aww.
Well, that's true.
Be still, my beating heart. Okay, now, here, let me see, okay, all right, let me see what I can do with the heat, yeah. All right, so,
Don't make it too.
it does say time to clean filter on the thing, so.
Already? They must have turned it on when they first got this in here. Those guys were working with.
It should be going on heat now, so.
Wouldn't it be on heat?
Well, I didn't turn it up very high, so. All right. Okay, I'll turn the heat down a couple degrees. There we go. That should be good. All right. Okay, so we've got our reactions, and now it's time to draw our shear and moment diagrams. I mean, ultimately, we're after the moment, but we've got to draw the shear first. Okay. What's that? Well, kinda. All right. So I think you all might like this. So the first thing that I'm going to do is I'm going to take my little image and I'm going to draw some, I guess, some dashed lines everywhere that we have a point of interest. I know it's a little messy on the screen. It's my first time trying to do dashed lines. Okay, so now what I'm going to do is I've got a big solid line here, and we're going to start off with the shear diagram. Okay. All right. Let's see. Maybe I can erase that a little bit.
So we don't draw a line through the 64 kip?
What's that?
We don't draw a line through the 64 kip point?
What do you mean? No. I'm just here. That black line, which it's a little thick. I'm gonna make it a little thinner. That black line is just the like the 0 on the shear diagram. That's all that is.
I'm talking about your vertical lines. Would you not consider this?
Didn't I? Right here. And that's what that one is. Like this one's the edge of the beam. That's AY. That's where the 20 kips is. That's where the distributed load starts. That's BY, and that's the other end of the beam.
You can't do where you diverged it from that point load because you get like a cylinder. That's why he didn't do that.
Okay, all right, okay. Now I get what you're asking. All right. And what Jacob said was exactly right. This 36 kips and those 64 kips, I created those to make the moment calculation easier, but in the end they don't exist. Okay. So maybe what I should do right now is go up here, and for clarity's sake, I should probably like erase all of this, because that's not really going on. Okay. So, everybody good? Now, when you're drawing a shear diagram, literally just look at the beam and do what it tells you, okay? So I'm sitting here looking at the beam, and we've got 6 kips per foot acting over a distance of 6 feet. So that's 36 kips, right? And it's pointing down. So it's saying, Greg, go down. All right, I'll go down. Okay, so it went down. Okay? And that distance is 36. So it went from 0 to 36. Okay? And now there's this 64.67 kip force. It's like, Greg, go up. All right, chill out. So I go up 64.67. And if I'm at, and maybe I should put, keep my sign here and put negative because I went down. If I'm at negative 36 and I went up 60.67, where am I at? Okay. Everybody good? Now I follow this over and I got nothing going on. It's saying, okay, Greg, you can relax for a little bit. All right, all right. Whoa, go down 20 kips. All right, okay. So I go down 20 kips. So if I'm at 28.67 and I go down 20 kips, that puts me at 8.67, right? So now it's smooth sailing. It's smooth sailing, right? And then now we hit a distributed load, right? So I go down 4 kips per feet. Now I'm ultimately going to go down for 10 feet, okay? So what 4 times 10 is 40, right? So if I'm at 8.67 and I go down 40, what's that going to put me at? Maybe somewhere like that? That's supposed to be a straight line. Right? Then it's saying, whoa, dude, you got to go up, like 55 kips. All right, I'll go up. Calm down. So if I go up 55 kips, what's that going to put me at? 24. And then what's the rest of the beam telling me to do? Go back down to 0. Okay, so there's a check. You better start and end at 0. And there's your shear diagram. Pretty good? Yeah. Okay, so tell you what, in order to keep this, clear on the screen, let's do this. I'm going to put these little like green lines in there, and we'll say this is 1, 2, 3, 4, 5, 6. I broke it up into simple shapes, and everything is numbered, okay? Everybody good? Now, since this thing is screencasting, you all mind if I erase all this stuff over here on the left? Or on the right, I mean. Not the left, we're using the left. But all this sum of moments and forces. All right. Now, I do know how this works. I can circle. I think that's cool. Yeah. Well, okay, so let's take, so I'll say shear diagram areas. Shear diagram areas. So area 1, that's a triangle, right? So it's 1/2 base times height. The base is 6 feet. The height is negative 36 kips. So that's half of 36, 18. 18 times 6 is negative 108, right? Okay. 2, that is, was that 28.67 times 4 feet, which is what? And that's positive, right? 3, okay. Now 3, we've got 8.67 times 4 feet, which is 34.68, and that is foot kips. Now, 4 and 5 are, we're going to have to discuss that a little bit. So I'm going to skip that for now. Let's just go ahead and do 6. 6 is simple. 6 is 1/2 24 times 6 feet, which is 1/2 24 is 12. 12 times 6 is 72. Right? Everybody good? Okay. So if that's good, let's look at 4 and 5. Let's sort of investigate that. So let's sort of zoom in on that point right here on the shear diagram. So we got that thing going on. We've got that. Four and 5. Okay. So when it comes to magnitudes, this is 8.67, and this is negative 31.33, right? Okay. So in order to calculate the areas of these triangles, what we're going to need is, we're going to need that distance, right? Like area base times height, we need the base. Okay? So in 10 feet, how much did I drop? 40 kips, right? So this is basically a glorified slope ratio. 40 kips over 10 feet equals 8.67 kips over x feet. Right? I think if it was 20 and negative 20, it'd be halfway through, right? Make sense? So this is just a glorified slope ratio. So if I drag that down a little bit, 40 kips times x equals, here I can do that in my head, 86.7 foot kips. And what is that? 2.17, close enough. All right. So if I want to, let me extend that out a little bit. Therefore, if I want to calculate the area of 4 and the area of 5, 4 is going to be 1/2 positive 8.67 kips times 2.17 feet. And 5 is going to be 1/2 negative 31.33 times what? What is that? 10 feet minus 2.17 feet? On the top? Which one's which?
The top's 2.17. Or 9.41, sorry, I was looking wrong there. Sorry, you do it up here. I was looking at the X height.
Now I'm doing it. All right, top one.
9.41.
And the bottom?
Negative 138.32.
$122.66. I'm gonna trust you. So far, so good? Okay. If that's the case, then I'm going to go ahead and draw a line right here and start my moment diagram. Okay. So here's how I'm going to do this, okay? So watch this. This is my secret to doing the moment diagram, okay? So, all right, we start off at 0, okay? Now, area number 1, let me scroll up. Area number 1 was negative 108, right? So that means between here and this first point, I got to be at negative 108, okay? Now, how do I get there? I look at the shear diagram. See how the shear diagram goes from a little to a lot? Like the value goes from a little to a lot? Does everybody see that? Well, that means the slope of the moment diagram goes a little to a lot. So you can think about it like this. Little to a lot, little to a lot. That's all there is to it. Because it's that relationship between shear and moment. Let me see if I can.
So you're basically integrating the shear diagram.
Basically, that's what you're doing. That's what a moment diagram is. Moment is the integral of shear. That's what it is. Okay, now, all right, so let's watch this. Okay, so from point 1 to point 2, I go up positive 114.68, okay? So if I'm at negative 108 and I go up 114.68, where am I at? Okay, yeah, so that's going to be like right there. 6.68. Okay? Now, what does the shear diagram look like in that region? It's constant, right? Constant shear diagram, constant slope. So that's my straight line. Okay? Next one. We have area 3 is plus 34.68. So if I'm at 6.68, I go up 34.68. What's that put me at? $41.36, and what's that going to look like? Straight line. A lot shallower because in that same distance, there's less change in shear. All right? Hold on, let me move that. I'm going to need the space. That's 41.34. Now, let's look what happens here. So I'm going to draw another little dashed line, sort of like that. So let's look at this. So our shear diagram is consistently going down, okay? But this little segment number 4 right here, would you agree that it's going a lot to a little? The magnitude, it's going a lot to a little. So the slope is going to go a lot to a little. See that? And if it's at 41.34 and we go up, what is it? 9.41, what's that going to put us at? All right? And that's rounded. And then for shape number 5, I'm at 50.77. I drop down 122.66. What's that put me at? Negative 71.89. So somewhere about like there, negative 71.89. So we go about like that, right? And then our last shape, how much should we go up? We should go up 71.89, right? And we're ultimately going to go up what? 72? The difference, that's just rounding. That's just everybody's calculators operating differently and people carrying things differently. So if we want, we can just say going up to 0. And again, that's curved. Make sense? All right. Before we continue, how are you all feeling about moment diagrams and shear diagrams now? A little more comfortable? A little more?
Better know that like that was what I did. Then I had rooftop one.
I tell you, students that are in calculus, they had it. I mean, they're up to their limit with that stuff. I mean, you get it? Up to your limit.
What were the other ones?
But remember, you know, like if you're in mechanics of deformable bodies, I mean, don't let the stress get to you in that class. I mean, you know, or especially like in fluids, because, I mean, the pressure builds in there, but I'm going to tell you. It's too late, I know. Yeah, it's screencasting, all this. I mean, it'll automatically go as soon as we're done. No, not really. The point of this example was to just go through a full-blown shear moment diagram start to finish.
Well, you could ideally stop with shear, do the calculations for 1 through 4.
Well, before we go on and start talking about strategy, let's just go back to the problem and see if we know what the answer is. The problem was, what is the largest magnitude of bending moment? What's the answer? The magnitude of bending moment on our moment diagram, 108. It's D. That's the largest number, the largest magnitude of bending moment. So let's make sure we know that. Now, as for strategy, you know, yeah, you could start adding up your areas and kind of see that. I wanted to make sure everybody understood the contours and whatnot. But beyond this, I mean, you really kind of just need to go through the motions. All right.
Well, you might need to know it. It might not ask the same question as you might need the moment diagram.
Yeah, you might, yeah.
Okay, so correct me if I'm wrong, but it's been said that the FE questions are designed for like 3 minutes apiece.
3 or 4. This is a longer question.
Okay.
This is longer. And
This is one that you probably want to flag and come back to,
yeah.
even if you do know how to do it.
Yeah, because it's going to take a while. Some of the things on the FE, there are tricks to do that might go quicker. This one, you might need to take a little bit of time.
Quit a little early on this one too. Once you realize that we had a moment of 114, it doesn't matter if the other ones go higher because the maximum value in the answer is 108.
That's a good point. That's another good point. But you still have to go through and do the reactions, do the shear diagram, do the areas under the shear. You still have to go through the motions. Yes, sir.
On the FE, are there questions that'll have like one problem that'll have multiple questions within, so you have to use like for instance, would it have a problem that says, hey, what's the maximum vertical, just different aspects of this?
I'll say this. There are sections that do that. One of the sections that pops up in my head is when you do the section on statistics. You a data set and say what is most nearly the mean and standard deviation. So they'll give you a bunch of mean values and then a bunch of standard deviation values, and you have to do both, which I know we're not talking about statistics, but let me tell you something. Learn the statistics functions on your Casio, because it's one of those things where a standard deviation is not very hard to calculate, but it takes a while. And if I give you 10 data points, you got to calculate the mean, then you got to calculate the variance, and you got to square it. You can just put numbers into your Casio and hit go, and it'll do it for you. So if you understand how your Casio works, it saves you a lot of time. I mean, a lot of time. So make sure you review that before you take the test.
Then when we take a break real quick.
I don't mind to take a few minutes. We can take a few minutes.
I know you can pause that.
Let me see. Yeah, I think I can. All right. Okay. All right. Yeah, I can pause it, and we can take a few minutes. Y'all want to take a few minutes? All right. Let's take a few minutes. Okay. So our next problem involves a deflection calculation, and these end up taking a little longer. So if you notice, the truss on this problem is far less intricate than the last one. Okay, and that's because when you're doing deflections, you have to solve the truss, and then you have to solve the truss again. So it kind of sucks from that regard. But one of the things you'll find about it is it ends up being kind of rote, and there's a little trick to this particular example that makes it a little easier. When it comes to deflection problems in general, trusses, there is only one way to do it effectively, and that's the unit load method, where you take a 1 kip load and place it on there. So we'll review that. For beams, there are 3 ways to do deflections that I think are effective. Okay? Number 1 is double integration, which I'm probably not going to cover, but I mean we can talk about it later or at another time if you're interested. You can do the unit load method, or you can do what we're going to do tonight, which is just use the manual, and it ends up being a lot quicker. Okay? So, but the unit load method definitely deserves a little bit of review, and that's what we are going to do tonight. Okay? So, let's go through the problem. So we have a plain truss. The problem statement was kind of nice in the fact that all the E values are the same and all the A values are the same, because that makes things a lot nicer. And what we want to do is determine the horizontal deflection at joint B. And we've got 4 choices. What is not the right answer? 0. It's not. I mean, obviously, if I push that truss, it's going to move. So it's not 0. Okay? So let's go to our screencast notebook thingy. Let's see if I can screen clip that. It's good enough. And then make that full screen. Now we can work with something. All right. Oh, I want to close that, but it didn't like me. Okay, so let's see if you all remember how this unit load method works. Now I'm going to change the problem up a little bit for the purposes of the explanation. Okay, let's say that I wanted to determine the vertical deflection at C. Okay, so if I wanted to determine the vertical deflection at C, I would have to do 2 separate analyses. I'd have to do an analysis of the real structure, which is what we're looking at right here, and then I'd have to do an analysis of a separate structure that looks like this. I'd have to do an analysis with a, let's say 1 kip load right there, right? So if I was wanting the deflection at C, this is what I would have to do. And I would take all the forces from this analysis, all the forces from this analysis, and I would calculate my deflection as the sum of all of my forces from the 1 kip structure, all my forces from the big structure, times L over AE. Y'all remember that? It's been I know you've done this before. It probably has been a while, but I know you've at least seen it. If not, no big deal. We'll go through it, and it'll be fairly straightforward. Okay? Now, this truss that I'm showing right here, this is if I was interested in the vertical deflection at C. I am not interested in that in this problem. What am I after in this problem? Horizontal deflection at B, right? So my real structure would be a horizontal 60 kip load on B, and my virtual structure would not be this, it would be this, right? That's my virtual structure, right? So let me ask you this. Do I need to do 2 separate truss analyses for this problem? No. I just take the results from the first analysis, divide them by 60, and I've got the results from the second analysis, right? It's all about strategy. There's no point in doing this truss analysis all over again, right? Everybody good? No point in doing it again. There's no, okay, so if I've got this structure that's 60 kips to the right and this structure 1 kips to the right, I don't need to do 2 separate analyses. I just take these results, divide them by 60.
So if they're asking you for the deflection at the point where the load is already applied,
Yeah, don't do it again, yeah.
divide by that load.
Yeah. And if they do, I mean, it's going to be a structure such that you can do it in the time frame. It's not going to be inherently complex. All right. Everybody good? It's not too bad. This is pretty straightforward. Again, this is if you're doing deflection. All right? Okay, so couple things. Let's go ahead and put the slope ratios on the members while we're thinking about it. So would you agree that these are 2 to 1, 2 to 1, and 1 to 1? Do you agree with that? Okay. Let's also pick some reaction or some directions for our support reactions. So, I don't know, D, what do you want to say, acting upwards? You want to assume down? It doesn't matter, yeah. Okay, what about AX? Should it go to the right or to the left? It should go to the left, because if 60 kips is going to the right, I mean, I can just look at that and say it's 60 kips going to the left, right? Now, I don't have any vertical forces, so it would make sense that if I have dy going up, I better have ay going down, because there are no vertical forces on the structure, right? That's a simple one. Good? All right. So, what do y'all want to do? Some moments at what? A? Now, one thing to keep in mind before we start attacking this problem, in order to do deflections, we need the force in every member, which is why this truss is a lot smaller. So, do we have any problem using method of joints on this? No, this one's fine to use method of joints because it's such a small truss. So I'm going to sum moments at A. Use my little table. So, summing moments at A, I got 60 kips acting at a moment arm of 20 feet. I'm going to go a little faster with this stuff since I think y'all are starting to get a little familiar with it. And I've got dy acting at a moment arm of 40 feet. Right? That's it, isn't it? So 60 times 20 is 1,200 equals dy times 40 feet. So therefore, dy is positive 30 kips, right? Or 30 kips acting up, right? Sum of forces in the x direction told me what AX was, so I don't even need to do that. Let me go ahead and write this 30 kips. And then sum of forces in the y direction. Do I even need to go through and do the math? It's 30 kips acting down, right? Okay. So far, so good? Any questions? So I'm going to use method of joints on this problem. Now, when you do method of joints, you have to start off at a location where you only have 2 unknowns, okay? Because when you're using method of joints, the difference between method of joints and method of sections is that when you're doing method of joints, all your forces all meet at the same point, okay? So because of that, you don't have sum of moments. Sum of moments doesn't work for you because all the forces go into the same point. There are no moments. So we have to pick a truss joint that only has 2 members to start. So if I look at this, I only have 2 places that I could start, A and D. Now, what seems simpler to deal with? D, because this has, vertical and horizontal components, so D seems a little simpler. I mean, you can do A, but the way that I'm showing you, it would be probably a little messier, so let's just go ahead and do D. So let's go through and look at joint D. So here's our joint. right? We have that is 1 to 2. Our unknown forces, I'll just go ahead and draw them. Well, actually, no, I'm going to wait to draw them. The only force on this member tells me that dy is 30 kips acting up, right? And that's all I've got. So far, so good? So this diagonal member is going to have a horizontal and vertical component. So it's going to be something like that and something like that. And that's going to be b dy. That's going to be b dx. What direction should I draw b dy? Down. Do I even need to do anything? Or just look at it and tell me what it is? See, this is starting to get pretty simple, isn't it? Now, b dx, do you need to do anything, or can you tell me what it is? Can anybody tell me what b dx is going to be? There you go. So this is to the right. All right, and what's going on with CD? Is it? What do we have going? Look at it. Look at our structure. So in the vertical, we got 30 down, 30 up. In the horizontal, 60 kips to the right means we got to have 60 kips to the left. That make sense? Because of this right here.
Oh, okay, I'm sorry.
No, that's fine. It's fine.
I was looking at it the other way. I was thinking BDY was...
No, yeah. See, this stuff's starting to get more familiar already. I mean, I'm teaching structural analysis right now, and I'm writing the sum of forces equations for every joint analysis that we do. We didn't even write any equations. We just looked at it, right? Simple stuff, right? Now, that's joint D. Where do you suggest that we go to next? C, because we only have this vertical and that diagonal over here. Let's look at C. You're going to see an interesting result when this all comes out in the end. All right? Let's look here. I can probably put that over here. Let's look at joint C. Joint C. So joint C, we've got this whole thing, that whole thing, like that. Now let's write the forces that we know. Do we know this force right here? All right. It is CD is 60 kips. What direction is it acting? To the right. Remember, we got that it was in tension on this joint. It better be in tension on that one. Okay? Now, we have an unknown force here, and this is a diagonal, so we have a vertical and a horizontal, and we know that that slope ratio is 1 to 2, right? So let's see what we got, okay? Let's just look at this diagram and see if we can see what makes sense. So this is ACX, and this is ACY, okay? Now, ACX and ACY. Can you tell me what ACX is? There we go. And if that is 60 kips, what's going on with ACY? And if I've got 30 kips going down, what's going on with BC? This isn't too complicated, is it? Simple stuff, isn't it? That's a good question. It goes from this slope ratio right here. So if 60 kips is to 2 as something is to 1, what is that something? 30. That's a great question.
Yeah, we've never done it like that. He made us actually solve for the angles and everything. This is way easier.
The reason why I don't like to do that is because here's what ends up happening. If you solve for the angle and then take the sine of that angle, or take the cosine of that angle, you're doing more number crunching. You know what this is right here? This slope ratio thing? This is SOHCAHTOA. That's what it is. Opposite over hypotenuse, adjacent. This is tangent. Opposite over adjacent. That's what that is, a slope ratio. It's opposite over adjacent. So that's why I do it that way. I think it's a whole lot easier. Yeah, and it is. AY is 30 going down, yeah. So you didn't even have to do any equilibrium. You just look at it. All right, now this is going to be really nifty. Watch this. Which joint do you want me to do, A or B? It doesn't matter. B. Okay, let's do joint B. You're going to like this. All right. So. All right. I'm going to need to. I know I'm going to need more room. So. Okay. So let's draw the joint. I'm going to scroll up and down a little bit so you all bear with me. So we got that, that, and that. Okay? All right. Now, let's start writing. Do we know this force right here? All right. That's BC, and that's 30 kips acting in what direction? Down. Okay? This member... Okay, watch this. Let's do this. Let's start off by putting in our slope ratios. So this is 1 to 2. That is 1 to 1. Okay? Now, we've got a horizontal and a... Ooh. That got away from me. We got a horizontal and a vertical here. So the horizontal here, what do we have for the horizontal? All right, 60 to the left, and we have what's going up? 30. Okay. Am I missing anything on this joint? There we go. Exactly. Make sure you don't forget that. Okay. So far, so good. So that means I got to have something here and here. What do I have? Pretty nifty how that works out. See, when you do your last joint analysis, what's going to happen if you're left with a diagonal member? What's going to happen is you can use sum of forces in the x direction and sum of forces in the y direction to directly write your numbers. And a check is, do they follow the slope ratio? And 1 to 1 or 0 to 0, it's the same comparison. Like it wouldn't make sense if you had 0 in the horizontal and then 30 in the vertical. You did something wrong. Make sense? So that's all there is to it. So
So much better.
Why didn't you graduate and start teaching earlier?
I literally cosine nonstop. Just over and over again.
I'm sorry I didn't give myself a stroke finishing my PhD on time. All right, so let's start writing down a summary. So, okay, let's summarize. Okay, how many members do we have in this truss? We got 5, right? AB, AC, BC, BD, and CD, right? So AB, AC, BC, BD, and CD, right? Right? Am I missing? Yeah. Okay. What's the force in AB? 0. Okay. Now, AC, how are we going to calculate AC? Okay, well, it's a diagonal, right? I got 60 kips and 30 kips. So what theorem, popular theorem am I going to use? Begins with a P, Pythagorean theorem. So this is just 60 kips squared plus 30 kips squared. Plug and chug, and what's that end up equaling?
67.08.
Okay, now, is that in compression or tension for AC? Look at your joint analysis right here. Tension, there we go. All right. BC. BC is, what is that? That's just 30 kips, right? And that is in tension. There we go. BD. BD is another one of those diagonals. The number is going to come out the same, right? Because it's the same slope ratio. We've got 60 kips squared plus 30 kips squared. And that is, whoop. All right. And then what's left? We've got CD, which is 60 kips and tension. Is everybody good? Everybody good? All right. Now, this is going to sound kind of silly, but we're going to take our time with this. All right. We'll draw this big table. All right, so member, we've got AB, AC, BC, CD, or wait, nope, I missed one. Okay. Everybody read that? All right. So, okay, our force in the member in kips, okay? Now I'm just going to show you what I'm going to do. Okay, ready? All right, so we have AB is 0. AC, I'm going to write that as positive 67.08. BC, I'm going to write that as positive 30. BD, negative 67.08. And CD, positive 60. Everybody good? All right. Those are the results from my real analysis, okay? Now, technically, I need to do another virtual analysis where I take a 1 kip load, put it at B, and do that all over again. But since the truss I just did already had a 1 kip load at B, how can I determine my virtual forces? I can take each of these numbers and divide it by what? 60. All right, so you all have calculators. You tell me what those are. That makes that minus 1.12. That would make this pretty good, right? Now, here's another caveat to doing deflection calculations. Deflection calculations with units can get messy, okay? The problem, okay? What are the units asking for in the problem? It's asking for deflection, and what does it express them in? Inches, okay? If I want to calculate deflections, I have to have delta equals the sum of F, big FL over AE. So if I want to start expressing member lengths, I need to do it in inches, okay? So let's look at our problem and let's see what the member lengths are, okay? Let's do the simple ones. Member BC, how long is member BC? Or, yeah, BC. 10. So, there we go. Make sense? Okay. CD is what? 240. And the others, what are we going to do? Well, you could do that, or, I mean, either one, Pythagorean theorem or the ratio. You all tell me, what's AB going to be? It's a 1-to-1, so it's 20 times the square root of 2 times 12 to convert it to inches. Well, actually, you know what? you can calculate that, but actually look at it. It doesn't matter because it's 0. So all we have to do is AC and BD, and they're both 20 across and 10 up, so they're both going to be the same length. So what do we got? So far, so good? All right. Now, let's look at the problem statement. We have to calculate little f, big F, L over AE. A is the same for all the members, right? It's what? 2 square inches. E is the same, right? It's 29,000 KSI, right? So what I can do is, to keep this simple, I can just say F, big F, L, and the units are going to be inch kips. All right, so the first row, that's 0, right? So what's this second row? 67.08 times 1.12 times 268.33. Right? And that's positive. What about the one below? Okay? Or let's say BD, it's going to be the same answer, right? 20,159.5. Positive or negative? Positive. See, you make sure you can keep track of your signs here. This is also more important when it's not asking for the deflection at the same point. You got to keep your tensions and compressions in sync. All right? BC, sum those up. What do you got? And we can keep it to single units. I mean, we don't have to be too accurate. And that's going to be inch kips, right? Because it's kips in the F. The big F is kips. The length is in inches. And little f, the virtual force, technically has no units. But it doesn't really matter. Okay. So we've got FFL, so therefore we can calculate our deflection pretty easily. It's the sum of little f, big F, L over AE, which is just 56.519 inch kips over 2.0 inches squared, 29,000 KSI. And what is delta? That's not too bad, is it? That's the thing. When I teach structural analysis, this might seem like an odd goal of mine, but if it's tedious for you, then I've done my job. Because some of the stuff that you do in this class, it's pretty repetitive. Because, I mean, it is what it is, you know? Okay. Before I move on, any questions? What's that?
Structural analysis, like this is bonded structural.
Yeah, unit load method where you put a 1 kip load on there. All right. But did this make sense? Now, again, if you were looking for the deflection at C, or like the vertical deflection at C, you would have to put a unit load at C, do the truss analysis again, and instead of just taking these numbers and dividing it by 60, you'd have a whole different set of numbers. Okay? Now, watch this. This is just for your edification so everybody knows. All right? So let's say I put a downward load, a downward 1 kip load on C. So it's going down. Okay? If I do my analysis and I get positive, positive, negative, positive, then that means I assumed the correct direction. If you assume the wrong direction and C actually deflects upward, then these will all be opposite signs because it all goes back to that fundamental tenet. You assume the direction, and if you're wrong, the answer comes out negative. Okay? So if all these signs are opposite, it's positive times negative, positive times negative, negative times positive, and so on. Does that make sense? So that's why that is what it is. All right. Everybody good? All right. I got one more fundamental structural analysis problem, and then I think we're good on the rote stuff, and we'll do some stuff that's a little more straightforward. Okay. So for the beams shown below, what is most nearly the vertical deflection at midspan? Okay. The beam is comprised of normal weight concrete, so it's 4,000 KSI concrete for the modulus of elasticity, and it has a moment of inertia of 1,000 inches to the fourth. So its I value is 1,000 inches to the fourth. Okay? And here's a number of answers. Just looking at these loads and these values, what probably isn't the answer? Hey, that's pretty small. What also probably isn't the answer? That's a lot of deflection for choice D. So just gut feeling, it's probably either B or C, you know? Right? Pretty straightforward, right? That's the thing. You really don't get many questions when it comes to the civil engineering portion where the answers aren't completely off the wall. I mean, that's for the mathematicians and the physicists. The engineering section is usually pretty down-to-earth stuff. Okay. All right, new page. Where's the new? Oh, there it is. Okay. A little screen clipping trick. All right. So here's the problem, and if one of the things to keep in mind is there's a couple ways to attack a problem like this. Okay, it's asking for the deflection at midspan. So one way of doing it is double integration. Which I don't recommend if you have point loads. If you have smooth continuous loads like distributed loads or triangular loads, that works great. It does not work great if you've got point loads. Okay? You could use conjugate beam. But I don't like conjugate beam if you've got distributed loads. Conjugate beam is for when you have a whole bunch of point loads because the geometry is a whole lot easier to handle from a conjugate beam standpoint than the integrals are from a double integration standpoint. Okay? A third way of doing it is the dummy load or the dummy or unit load method. In other words, we can calculate the deflection instead of summing up little f, big FL over AE, we can integrate little m, big M over EI dx from 0 to L. Okay? I don't like that either if you've got a function or a loading scenario that's got a bunch of discontinuities. Now this doesn't have a bunch of discontinuities, but it's enough that I think there's probably a much simpler way to do it, and that is use the manual. Okay. There are beam deflection formulas in the manual. My only note that I would make is make sure units are compatible. Okay? So you all have this this handout right here. Okay? I want you to turn to page 84 in the Mechanics of Materials handout. Okay? So, looking at this handout, I'm on case 1, 2, 3, 4, 5, 6. Does everybody see this? On the top of it, it says simply supported beam slopes and deflections. Okay? So, for this problem, I've got two different loads. I have a distributed load and I have a point load. So, how do you handle this? You use superposition. The deflection due to the loads on that screen equal the deflection due to the distributed load plus the deflection due to the point load. Okay? So let's talk about the distributed load first. Okay? So what is the deflection due to that distributed load? So we're talking about deflection at midspan. Now, you can ignore the signs on the table because we know it's going to deflect downward. So what's the deflection? Right? So let's just plug and chug. And let's just see what we get, okay? What's the distributed load? 2 kips per foot, is it? Yeah. Beam, how long is the beam? 24 feet? E is 4,000 KSI, and this is 1,000 inches to the fourth. Now, before we do any button crunching on the calculator, let's look at the units, okay? So what are we going to get from a unit standpoint? We're going to get kips per foot times feet to the fourth, right? Then we're going to get kips per inches squared times inches to the fourth, right? Okay, so what's going on with the kips? They cancel, right? So what do we have on the top? We have feet to the fourth over feet, so that's feet to the third, right? Okay, and on the bottom, what do I have? Inches squared. Everybody good? Now, this is a deflection, right? So what do I ultimately want this answer to come out in? Inches. So I've got feet cubed over inches squared. Wouldn't it be great if I had inches cubed over inches squared? Because then it would cancel, right? So I need to turn this, oh, it does not like me. I need to turn that into inches cubed. And how do I do that? Well, there we go. So this is, I can multiply it by a conversion factor, the fact that 12 inches equals 1 foot, because that's essentially multiplying by 1. But that's just 1 unit. I have to cube the whole thing. Right? Does that make sense? So if I go up to my deflection problem, about the whole thing, I have to multiply it by 12 cubed. Well, here, I'll make that simpler. So I'm not multiplying it by 12 cubed for willy-nilly. I'm doing that so that I get my answer in an appropriate unit system, in other words, inches. So you all have the button crunching going on. You tell me what we got.
3.7
3.73 inches. What do you think the answer to the problem is? It's probably C, right? It can't be B. A obviously can't be A or B, and D just doesn't sit right. Well, we can keep going if you want, but I mean 2 kips per foot over 24, that's 48 kips. Okay, 48 kips caused that much deflection. How is 20 kips going to cause 9 inches? Doesn't make any sense, does it? But we already know what the answer is, right? Everybody good? Now, if you want, we can go through and do the rest of the problem, but I have some other topics I want to cover, so let me just say this, okay? Let's look at the handout real quick. So if you look at the handout, I'm on case 2. Does everybody see case 2? Would you agree that this is case 2? 2 things. One, we have to use the elastic curve equation on the very right. The reason why is because this deflection in the center is only going to give me the deflection right here. Let me pull up the screen for the screencast. So that V at x equals A is only going to give me the deflection right there. I'm not after the deflection right here. I'm after the deflection at midspan. So it's at a different point. So because of that, you have to use the elastic curve. The only other thing worth mentioning is you just got to make sure you keep track of your B's and A's, okay? That elastic curve equation is only valid from between 0 and A for x. So ultimately what I'm getting at is that for this problem, you almost have to take the beam and mirror it and use x equals 12, A equals 14, and B equals 10. Make sense? Does that make sense?
Why 12? This, like I said, this is all.
Well, all I'm saying is okay, that equation is valid from, like, if you look at the elastic curve equation, okay, it would only be valid from x equals 0 to x equals 10, right? But we want to find deflection at x equals 12. So a way of doing that is just imagine it was backwards, okay? So this is A, this is B, and I want to find it from here, x equals 12. That's all I'm saying. So, everybody good? Okay. Now, I have one final topic that I definitely want to cover in here, and this doesn't even have anything to do with anything that you all probably even covered in structural analysis. Let me ask you a question. Hold on. If this is just for my curiosity's sake. Let me see if I can write on the PowerPoint. I think I can. Oh, no, I can't. Okay. Let me just see this. If I wrote this equation on the board, some of you are going to recognize it and some of you aren't. So I know who's going to recognize it. I'm curious about the ones who don't. I know my steel and concrete folks, they remember that. What is this? This is live load reduction, okay? So for those of you that weren't exposed to this, this is the live load reduction formula used to account for building loads. So to give you kind of an idea, if I remember correctly, the design load for a classroom, let's say, I think it's like 40 PSF. I think it's 40. It might be 60, but I can't remember. Now, to equate that in terms of people, the size of this room, to reach that design load, you'd probably need about 120 people in this room. When do you ever think there's going to be 120 people in this room? Never, okay? So the design codes specify a certain live load, but we are allowed to reduce that based on the probability that we're not going to see all that design load throughout its design life, and that's live load reduction. When you get to concrete design and steel design, you end up using factored loads that hold 1.2 times the dead plus 1.6 times the live. Okay? Well, you have to calculate your dead loads and your live loads in order to use that. So that's what this problem is about. Okay? Because it technically is structural analysis. It's not design. Okay? So let's go through the problem. All right. A floor system in a building uses 45-foot long floor beams spaced at 9 feet. Okay? The floor will be subjected to a service dead load of 50 psf and an unreduced service live load of 80 psf. Using LRFD load combinations, what is most nearly the maximum moment on the beam? If there's any one time that this little structural analysis page comes in handy, it's right now. Okay, so what we're going to try and do is determine the bending moment on this floor system. All right? So this actually is a fairly straightforward problem, but if you've never seen it, I want to arrest that right now. So let me go to my little notebook thingy. Let's full screen that. And let's use my little eraser trick. And boop. All right. Okay. So for this problem, it told us that the floor beams were 45 feet long, and it told us that those floor beams were spaced at 9 feet, right? Okay? Now, let's go to our sheet from the FE manual. So I'm looking at the page on the back, okay? Now, if you recall that KLL, that's a live load element factor. It's the ratio of the tributary area to the influence area, okay? Now, are we looking at a column or are we looking at a beam? Beam. So what's KLL? 2. All right? So let's keep going. All right. So I want to sort of draw this floor system out so to make sure everybody understands what's going on. So those of you who've had me for a structural engineering class know what my secret weapon of structural engineering is, and what is it? The samurai sword and or lightsaber if you're a sci-fi fan. So let's say I'm in this building, I take a samurai sword or a lightsaber and I chop right through the floor and I'm looking at it like this. I'm going to have, let's say, a floor slab that looks something about like that. And I'm going to have a bunch of floor beams spaced out like so, right? And those floor beams are running in and out of the screen, okay? So how far apart are those floor beams spaced? 9 feet. So far, so good? Okay, now, I'm going to pick any one of these beams, and I'm going to try and determine its tributary width. Now, if you haven't heard of this, tributary width is how much a given beam is responsible for. In other words, would a fair statement be that this beam is responsible for all the floor halfway over to the next one, halfway over to the next one? In other words, this shaded area right here, that is the part of that floor that that beam is responsible for. Halfway over and halfway over. So what is the tributary width of that beam? 9 feet. Oh. Tributary width is 9 feet. So now that's its tributary width. Its tributary is just the tributary width from an area perspective. In other words, the width times however long that extends. And how long is that area going to extend? 45 feet. The beam's 45 feet long, so it's going to be responsible for 9 by 45. So 9 by 45, therefore,
Does that take into account
What's up?
From my own knowledge, does that take into account like the width of walls and things like that? Because I mean,
Well,
stop right there.
no, that's a good point. When you get to partitions on the side, where you have walls and you have, curtain walls and you have spandrels and what have you, be a little careful with your calculation and at worst case be conservative. But I mean, yeah, you can handle this there as well. There are certain situations where you can't use live load reduction. For instance, you can't use live load reduction if you're designing, let's say, the balcony in the new Dallas Cowboys Stadium, because the live load might be like 100 PSF. It might actually see 100 PSF, especially like if you had like a fire alarm or something. So you can't reduce that at all, because if you do and it actually sees that load, people aren't going to have a good day at the football game. Okay, so.
Well, what if we had like a section? So this room, hypothetically, is perfectly square, and I have a row of desks that nobody goes under, and I know that's attributed to dead load, right?
Desks are related to occupancy. That's live load.
Okay.
Because live load is occupancy. That's what the building is being used for. So if this is being used as a classroom, then the desks count. So, yeah. All right. Let's go on with this, and let's go through our structural loading. So for this problem, we were given a dead load of what, 50 PSF, and a live load, unreduced, of 80 PSF, right? Everybody good? No, you never reduce dead load because it's always there. Live load, you're reducing it based on the probability that it isn't there. Dead load consists of the structure self-weight, and structure isn't going anywhere. So you never reduce live load. Speaking of reducing live load, it would be the original live load times 0.25 plus 15 over square root of K LLAT. And again, this is one of those empirical relationships. You cannot derive this. It just fits the test data, fits the observations. So 80 PSF, everything's in US units, 0.25 plus 15, 2 times 405 feet squared. And what is that?
62.16.
All right. Okay. Now, I can go ahead and if I want, if I have a dead load and a live load, I can factor that right now and determine a factored load. What is my load combo that's going to govern?
1.2 times the plus 1.6 times the
Now, if you're wondering where those come from over here. Those are LRFD load combos that take into account statistical uncertainty with each load. Now, look at the numbers, okay? We're only given dead and live loads. So if you look through the variables, the only one that's going to govern is either the first one or the second one. And if I start plugging in numbers, this is what, 50? That's, what is that? It's our 62.16? I'm getting tired. That's what it is.
159.46.
Okay. If you recall, you basically are supposed to cycle through each of these load combos and take the largest one. Now, what's going to be larger, that or 1.4 times 50? That. So there's no reason to check the others. All right. Now, keep in mind that what this means, what we're looking at right now, is we're going to test my 3D art skills. So let's say here's the floor, and it's going like that. What that means is that we have a factored load of 159.46 PSF. That's a pressure load acting on the whole floor. So that's everywhere. Now, ultimately, what I want to do is for a given beam, I only want the floor load on that beam. Okay? So what I'm going to do is I'm going to take that pressure load, distribute it to that beam. If I take a pressure load and distribute it to a single beam, what am I getting? A uniformly distributed load. And what is that uniformly distributed load going to be? It is going to be our pressure load times the tributary width, which is 159.46 PSF times the tributary width of 9 feet, which is what?
1435.48.
And that's pounds per foot, or 435 kips per foot. All right? So ultimately, here's my problem, okay? I've got a beam, I've got, come on. Find me that way. I have a distributed load acting on that beam, W. And that beam is L long. Now, if you don't remember the formula, which if you had me for steel or concrete design, I would be very disappointed if you didn't, there should be formulas in the manual. I think there are. Well, I'll be. There's not. They just have the deflections. They don't have the moments. Well, can you all draw the moment diagram for that? Okay. Let's say you let's say you don't want to draw the moment diagram. Who can tell me what the maximum moment for this situation is going to be?
WL squared divided by 2. No, it's over 8.
There we go. It's over 8. Now, why is it over 8? Watch this. Would you agree that your shear diagram is going to look like that? Watch this. Okay. That distance is L over 2. This height, that's the reaction, right? What's that reaction for this beam? Is it WL over 2? Like half the load over here, half the load over there? What's the area of this triangle? It's 1/2 base times height. 1 times L times W times L. 2 times 2 times 2. 8. Back to our problem of interest. 1.435 kips per foot times 45 feet. That is squared over 8. What is M max? Hold on. I don't have a microphone. Hold on. Yeah, I know. Yeah, that would have been better because that was probably the most awkward way anybody could have done that. Before we close it off for the night, was this helpful? Okay. All right. Good. Does anybody have any questions about what we've covered tonight? Okay. I'm seeing the writing on the wall, and I'm thinking influence lines. Another day, another time. That's no big deal. At most, it's one question on the test. Maybe later, maybe next year with this video around, I'll be able to do some of the more advanced topics and say, just watch my old one for any of this other more fundamental stuff. An influence line is if you take a 1 kip load and move it across the structure, what does it react? Is everybody good? All right. Thank you for that. 'Cause